Today we're going to be talking more specifically about the different parts of a wave and what that wave looks like. Now there are more types than the two that we're going to discuss today, but these are the two that are going to be a part of our discussion when we're talking about sound and light, and they're the most commonly understood waves, although there are some other types as well. So the first type of wave that we're going to talk about is a transverse wave. And light is commonly thought of as a transverse wave. Now, if I look at a transverse wave, again, it would be sort of like if you took a rope and you attached it to one end and you kind of shake it up and down, and then you will see those types of waves move through it. And as I said before, I've got some other video links for you, and if you can actually see these types of waves being produced, it will make it a whole lot more clear, so please don't skip those. There's a particularly good one that I've linked you to today where it shows you people making these types of waves with a slinky. Both of these types of waves can be made very easily with a slinky. In fact, if you have a slinky at home, you can do this yourself either by kind of taking the slinky and moving it up and down, or taking the coils and just shoving them, and then as they oscillate back and forth, that will make the second type of wave that we're going to talk about. So if you have a slinky, I would encourage you to try it. At the very least, do make sure you watch the other videos that I have linked you to. So we're going to start out by talking about a transverse wave. And this is the type of wave that people think about that maybe moves through water. It's not exactly the same as a water wave. That's actually called a surface wave, which you've read about in your book. And I have sent you a link to what surface waves look like as well. So, but this is a similar type of wave. So when you talk about a transverse wave has a crest up at the top, and then down at the very bottom, it has what's called a trough. And so this is also going to have a rest or an equilibrium position, which is going to be right in the middle of the wave. And so just like we talked about before, the area of maximum displacement is called the amplitude, not the altitude. It's called the amplitude. So the distance from the crest to the equilibrium position would be the amplitude, or you could also measure it from the trough to the equilibrium position, and that will be classified as the altitude as well. The distance is going to be the same in both cases. Now, what I want you to be aware of is that you may also hear something about a wave height, which is more common for people who are on the ocean to talk about. And so the wave height is going to be from the crest all the way down to the trough. So this is the wave height, but it is not the same as the amplitude. Obviously, the wave height is 2 times whatever the amplitude is going to be. The amplitude is just going to be half. The other important piece of a wave that we need to understand here is called the wavelength. And you can measure the wavelength between two identical points on successive waves. So the easiest place to measure it is from a crest to another crest, or from a trough to a trough. I could measure it from here to here because those would be the same point on the wave, but say again, it's easier to measure from a crest to a crest. So if you're sitting at the beach and you're watching the waves come in, normally what your eye sees is the high point, and so you're watching the crests, the wave crests come in, and so what you're seeing there from one crest to the next crest is called the wavelength. So this is the wavelength, and we often use the lowercase Greek letter lambda, which I make like that, for the wavelength, and we'll be using that a little bit later on. So I'm going to go ahead and introduce it here so that you can see it. So that is the wavelength. And again, I could do a wavelength from a trough to a trough as well, as long as the points on the waves are the same. Now be careful, you can't go from here to here because that's not long enough. If you're on the downside of the wave here, then you've got to be on the downside of the wave over here to measure an accurate wavelength. Okay, A period is going to be from the time one crest passes to the time the next crest passes. So that's how you're going to get a period timed in a wave, is watching from one crest to the next crest, or from one trough to the next trough. But as I said, if you're sitting on the beach, it's much easier to count crests or to time how quickly the waves are coming in based on the crest. Okay, the other type of wave is the same type of wave that is a sound wave, and it's called a longitudinal wave. And it's really hard to depict this on a whiteboard because you have to have a picture in your head of what it looks like. So again, make sure you check that other video out. But what it looks like is if you took a slinky and you stretched it out, and then it's stretched out flat on a table, and then you give it a push. And then the slinky just kind of oscillates back and forth. It doesn't go up and down, but it oscillates back and forth like this. And so in that type of thing, you have a compression place of all of your coils that's moving down, and then that compression place is going to move back. So the points here, in place of a crest and a trough, here I have a compression, and then the part where the coils are spread out is called a rarefaction. So a compression would be similar to a crest, a rarefaction would be similar to a trough in a transverse wave. So the wavelength here would be from one compression to the next compression. Okay, so there is your wavelength on what is called a longitudinal wave. Now, one big thing about these two types of waves is which way the particles move when the wave passes through the material. So both of these types of waves we're going to be thinking of in this particular discussion as mechanical waves, because we're going to talk about which way the particles move. And again, it's really hard to show you this with a still drawing, so make sure you check out the computer animation also that I sent you on another link, because it does a really good job of showing you how the particles move. But in a transverse wave, the particles are actually going to bounce up and down, which if you think about a duck on a pond, and he's just sitting there, and as the waves pass by him, you can see the duck kind of bouncing up and down on the wave. So the particles will bounce up and down on a transverse wave. However, on a longitudinal wave, again, if you can see that slinky in your mind kind of stretched out on the table, and things are moving back and forth, here the particles in the path of the wave, if the wave is moving this direction, the particles are going to go this way. So here the particles are moving, they move perpendicular to the direction of the wave. So if the wave is going this way, the particles are going to bounce up and down this way. Here, if the wave is moving this way, the particles are going to move back and forth this way. So here, the particles are going to move parallel to the wave motion. So again, those are very different from one another, in fact, completely opposite from one another. So make sure you check out the computer animation that I sent you, because they will highlight the particles, and you'll be able to see very clearly that in a transverse wave, the particles move perpendicular, and in a longitudinal wave, the particles are moving back and forth. So make sure you check out those other videos and really enjoy looking at those, and then you'll be analyzing some of that today as well.